Okay, welcome to 4Keys Physics. So I'm back again with this advanced level physics problem, static equilibrium, commonly referred to as the ladder problem. So we have a question that we'd like to explore here. You're given that diagram, and the question is, what is the force of friction between the ground and the ladder? So in order for the ladder to stand like that, our forces must be in equilibrium. There is no movement, so the forces that are acting in the x direction and the forces that are acting in the y direction must be in equilibrium. We also have a force that is called torque. So our torque is supposed to be in equilibrium again in this scenario. So let's label the forces that are there. So that would be the frictional force that we're concerned with. Take note that the direction of the friction force is to my left. So the ladder is not sliding at that point, at that pivot. That means that there's a force that is keeping it in place, and that is the frictional force that we're concerned with. It's acting to my right. And like I said, all the forces that are acting in the x direction must be equal to 0 in this case. So, and also the forces that are acting in the y direction must be equal to 0 in order for the ladder to stand and not move. And our torques must be equal to 0 again. They must be in equilibrium. The torque in the clockwise direction and the torque in the anti-clockwise direction. You should remember that the torque in the clockwise direction is negative and that in the anti-clockwise direction is positive. Okay, let's move on. We know that there's a force acting downwards from the mass of the person on the ladder. So that makes one of the forces acting in the y direction in a negative direction here, because it's going down due to gravity. And we also know that the ladder has a mass. So in this case, the mass of the ladder is 17 kilograms. So there's a force due to gravity, which is mgl in this case, the force due to the mass of the ladder. So we have those two forces acting in the y direction, in the negative direction, and those must balance out with another force. In this case, the force that we're talking about is the normal force, which is acting upwards. So those forces must be equal to 0 because there's no movement in the y direction. So we have to acknowledge that. And in the x direction, we have a force that is coming from the wall. The ladder is leaning on the wall at that point, and there must be a force which is coming from the wall pushing the ladder in that direction so that it's not able to move. So that's our FW there. We must also know the distance that we call the lever arm in order for us to calculate our torque. And the lever arm here for the force due to the ladder is 1.1 meters. So you must be able to label that distance that I've shown in dotted lines there. And we have another lever arm for the force that is coming from the person standing on the ladder, and it's 1.6. These two lever arms are different. So these will enable us to calculate the torque that is due to the mass of the ladder, and the other one that is due to the mass of the person standing on the ladder. Okay. We must also know that the force of friction that we're concerned about is balancing out with the force that is coming from the wall. As you can see, the frictional force is acting to my left, the force on the wall is acting to my right, and the ladder is not moving. So these two forces are equal. And since there are only two forces there, when we subtract those two forces, we get is 0. It means that those two forces are actually equal. So, and then we said the normal force is balancing out with our mg, the mass of the person, times the acceleration due to gravity, minus the mass of the ladder times acceleration due to gravity. So if we subtract the normal forces, the normal force which is balancing out with these two forces, we get a 0. So we have our torque equation, which you can use to calculate the torque, but unfortunately we're not going to be able to do this using trigonometry because we are not given the angles, we are not given the information that we need. So instead we're going to use this other equation, which is the torque is equal to the lever arm times the force. So let's apply that to the three forces that we have, our TP, our T ladder, and TW. So when you do that, we're going to say for the person, we have our XP, which is our lever arm. Like I said, this is 1.6, if you still remember. Finally, our lever arm for the force coming from the wall. And the lever arm for the force coming from the wall, because this force is perpendicular to the lever arm there, it's going to be 5.5, which is the distance from the ground to the point where the force is acting. So our lever arm is 5.5 for the force that is on the wall. Okay, so what we simply have to do here is substitute what we know so that we solve for the force on the wall. And if you remember what we said, that is our FW is equal to the frictional force. So if we solve for FW, then automatically we would have figured out our frictional force. So let's substitute what we know, and if we rearrange that equation, we're going to have this equation. We move everything else to the right, and we divide by y, which is our lever arm. And if we substitute what we know, we have all the variables here except for FW, and we're going to realize that our force on the wall is 247 newtons, and this is equal to our frictional force.